Starts.
Okay, you can start.
Okay. Welcome everyone to the ICNP session number 4 on network measurement and emulation. Today we have 3 really good papers, including the best paper of the conference in this session. So just one thing, I'm going to ask you to use the question and answer tab to post questions, and then at the end of the talk, I will look at those questions. I'll ask some of those questions, and then after I've done that, I'll invite people to ask questions live. Okay, so use the in other words, use the online question thing if you're a little bit shy and you don't want to ask a live question, and I'll ask it for you. Otherwise, you can ask it yourself after I've done the online questions, okay? So the very first talk that we have today is by Jiamin Chao, and I'm gonna let each speaker introduce themselves.
Okay. Hi, everyone. I'm Jiamin Cao from Tsinghua University, and currently I'm a third-year PhD student, and my research interests include the programmable network and network verification. So should I continue to present my work? Okay, can you see the slides?
Yes, I can.
Okay, today I'm going to present our work, TurboNet, faithfully emulating networks with programmable switches. This is a joint work with Zhou, Professor Ying Liu, Professor Mingwei Xu, and Yongkai Zhou. When we have new network designs, we may first conduct network experiments, and the network experiment platform should satisfy 3 requirements. First, they should accurately mimic the behaviors of real networks. And second, they should support flexible customization of topologies and network properties. And third, they should easily scale to meet increasing network bandwidth and sizes. Given these 3 requirements, let's look at the existing network experiment platforms. First, the simulators leverage CPU to model the real networks. They support flexible customization and can easily scale to large networks, but the model cannot fully represent the real networks. Second, the emulators run the same code on CPU as real platforms. They can be customized like simulators. However, their experiment sizes rely on the available CPU cycles and memory. Thus, they cannot provide accurate performance results for high-speed networks. Third, we can also build testbeds composed of real devices. The testbeds provide fidelity guarantees, but may not support flexible topologies, forwarding behaviors, and metrics. Furthermore, as networks evolve, the testbeds shall be upgraded correspondingly. So in summary, there remains a gap between existing network experiment approaches and real networks. To address this gap, we explore a new direction for network experiments, emulating large networks with one programmable switch. So why programmable switch? The programmable switch conducts reconfigurable packet processing on data planes with high bandwidth. With this flexibility and high bandwidth, we may customize the high-speed networks and validate our design. Therefore, our goal is to faithfully emulate both network data plane and control plane. For data plane, we should be able to emulate various topologies and network metrics such as link delay and link loss. For control plane, we should support different routing methods such as static routing, distributed routing agents, and centralized routing controller. This is my talk outline. The motivation has just been introduced. Next, I will introduce the TurboNet architecture and workflow, and I will show how to emulate the data plane and control plane. I will also present some evaluation results. TurboNet can be implemented using one programmable switch. First, operators describe their network emulation tasks. Like this, we provide a set of API. Operators can then use the API to describe the emulated network by adding switches, adding ports, adding links, and then setting the corresponding metrics. Then the TurboNet should translate this input task into configurations on the programmable switch. For data plane, TurboNet compiler should generate the P4 program, the switch configurations, and table entries to construct topologies with specified performance metrics. For control plane emulation, TurboNet may add or delete routing entries for static routing, create containers as routing agents for distributed routing, or establish the control channel with a remote controller for centralized routing. Finally, operators can conduct experiments on the emulated topology. Here comes the question, how to emulate the network on the programmable switch. So next, I will present how TurboNet emulates the data plane and control plane. The data plane emulation means forwarding packets in a network with specified performance. Specifically, two questions need to be answered. The first is about the topology emulation, how to emulate various topologies. The second is about the metric emulation, how to emulate the performance metrics to make the emulated network behave like real network. Let's first look at the topology emulation. Our key idea is to split one programmable switch into multiple emulated switches. Now we want to emulate the left topology on the right programmable switch. First, we map each port in the input topology, that is port X1 to X6, to an individual port on the programmable switch, port Y1 to Y6. Then each switch in the input topology is also mapped to a set of ports. For example, when packets are received from port Y1, they are considered to arrive at X1 on switch 1. Assume that switch 1 forward packets from X1 to X2, then we just need to define tables that forward packets from Y1 to Y2. This is the switch emulation. Next, for link emulation, a naive method is to manually connect two ports on the same link with a cable, such as port Y2 and Y3. But this is too troublesome when the network is complex. So we solve this while configuring the ports as loopback mode. For example, when switch 1 sends packets to switch 2, the packets should be sent to port Y2 on the programmable switch. Since Y2 is a loopback port, the packets should be received by Y2 again. The loopback port Y2 can be taken as a link which transfer packets from Y2 to Y3. That is, the packets are considered to arrive at Y3 on switch 2. Then switch 2 can process these packets as if they are from port X3. So in summary, the switch emulation includes 3 parts. First, after receiving packets, the physical to logical part, and that is the P2L port mapper, matches with the ingress port and outputs the corresponding switch and port in the input topology. And second, the emulated switch part implements the policy of each emulated switch, which are defined by users. And third, the L2P, the logical to physical port mapper part, reverts the egress port to the port on the programmable switch. The link emulation module has similar processing logic to the switch emulation, including the P2L port mapper to identify the current link, and the emulated link part for link metric emulation. With this port mapper, it's apparent that the emulated size is limited by the port number. Let's take the Tofino switch as an example. Given that there are 64 port groups in one switch, and each port group can be subdivided to 1, 2, or 4 subports, then the total port number can never exceed 64 times 4. So can we emulate larger topologies? We find that there are 32 queues under each port group, and altogether 64 times 32 queues in one programmable switch, which is 8 times larger than the port number. Therefore, we propose the queue mapper and map each port directly to some queues. Then how do we perform the port or queue mapping? We formalize these two problems into ILP problems. With this user input, we will solve the mapping problems and then generate the corresponding table entries and switch configurations for topology emulation. More details can be found in our paper. Next, let's look at symmetric emulation. Here we mainly present the link loss and link delay emulation, which are two important network properties. We also provide background traffic emulation in our paper to inject background traffic to the network, but I will not expand this part due to time. The link metric emulation resides at this emulated link part. When receiving packets from a port, we first identify the current link from the P2L mapper part and then perform the corresponding link metric emulation in this emulated link part. For link loss emulation, P4 has no direct method to perform an action according to a probability. However, it provides a primitive to generate a random number from a given range. For a given loss rate, we can calculate a threshold so that the probability that this random number being larger than the threshold is just the loss rate. Then we can drop packets according to our desired probability. So this is the link loss emulation. Next, let's look at the link delay emulation. Link delay emulation is a challenge because it's very difficult to keep packets in programmable switch. Look at link 1 in this picture. The loopback port Y2 acts as a link to transfer packets from switch 1 to switch 2. The loopback delay is very small, often in nanosecond level. To emulate larger link delay, we should insert extra delay before packets are processed by switch 2. But how to keep packets in programmable switches? An observation for us is that the queuing time is in proportion to the queue depth. Therefore, we can maintain the queue depth to achieve target queuing time. The high-level idea is to first implement delayed queues with desired queuing time, and then send packets to the delayed queues to emulate the target link delay. Then how to implement the delayed queue? The key idea for delayed queue is to inject packets to the delayed queue to maintain the target queuing time. We place a register queue time in the egress pipeline to record the up-to-date queuing time. When packets are dequeued from the delayed queue, they update the queue time. Meanwhile, we use the internal packet generator to inject backup packets to the switch, decide whether to send these packets to the delayed queue based on the queuing time. If the queue time value is smaller than our target value, they should go to the delayed queue to increase the queuing time. As the queuing time has upper limits, packets may go to multiple delayed queues for higher delay. The above is our idea for link delay emulation. There are more detailed analysis in our paper, including the resource consumption and the emulation accuracy discussion. Next, let's look at the control plane emulation. The control plane mimics how routing protocols or programs control the networks. To accurately emulate the control plane behaviors, we provide both static routing and dynamic routing. The routing tables reside at this emulated switch part. Users can define their own routing policies for each emulated switch by specifying the routing tables. For each received packet, we first acquire the current switch index and the ingress port from the P2L mapper part, and then performs the corresponding routing policy, and finally transform the logical egress port to the practical egress port on the programmable switch. For static routing, the routing entries are added or deleted manually. Users don't need to know how the ports are mapped, but just need to call the API to manage the table entries in their own emulated switches. For dynamic routing, we support both distributed routing and centralized routing. For distributed routing, we create a separate container as a routing agent for each emulated switch. Operators can specify the routing protocol and run the routing algorithm in routing agents. The routing agents inject routing messages to the emulated switch and manage the routing entries on the emulated switch. We have a TurboNet runtime on the switch CPU as a proxy to transfer routing messages and routing entries. We also support centralized routing with a real remote controller. Operators can run their routing program on the controller. Each emulated switch has a local control plane on TurboNet runtime to establish a control channel with the controller. The controller collects network status from local control planes, calculates routing entries, and distributes the entries to different local control planes. Now I have introduced the TurboNet design on both data plane and control plane. Next, I will give some evaluation results to show TurboNet's emulating capability. We evaluate TurboNet with one Tofino switch and two servers. The switch has two packet processing pipelines for 3.2 Tbps port bandwidth. We first use TurboNet to emulate various data center topologies such as the factory and VL2, and also the internet topologies from the Internet Topology Zhou dataset. We evaluate the topology emulating capability of TurboNet for both port mapper and queue mapper. We can see that on the 4-pipe switch, the port mapper can only emulate the 4-array factory, while the queue mapper can emulate the 8-array factory. Also, queue mapper can emulate 60 more internet topologies than the port mapper on the 2-pipe switch. This is because that these 60 topologies have many links with more bandwidth, which can be further mapped to queues using the queue mapper. This figure shows the link loss emulating accuracy using the 32-bit random number generation. We set different loss rates and check the deviation of practical losses from expected ones. We can see that when the expected loss changes from 0.1 to 10 to the power of -8, the relative error is always smaller than 1%. We also test the practical link delay when emulating different target link delay. The left figure shows the one-pass delay. Packets pass a delayed queue only once. As the expected delay ranges from 0.2 millisecond to 1 millisecond, the practical delay presents minimal difference from the expected delay, and the standard deviation is always smaller than 9 microseconds. The right figure shows the multipass delay. Packets pass the delayed queues more than once. As we can see, with packets passing the delayed queues more, the delay variations also increase, but the relative standard deviation is always smaller than 0.9%. For the control plane evaluation, we mainly test the distributed routing because it requires more resources since an individual routing agent is created for each router. These two figures show the CPU and memory usage. The CPU usage peaks in the first few minutes and then decreases, while the memory usage changes differently which increases at first and then remains stable. We can see that TurboNet can easily support almost 200 BGP routing agents with 25% peak CPU usage. Okay, now let me conclude my presentation. TurboNet is a network experiment platform that leverages one programmable switch to faithfully emulate both the data plane and control plane. In our future work, we will combine more programmable switches to emulate larger networks with more complex network functions. Furthermore, we will consider how to accommodate to dynamically changing network emulation requirements so that we will not interrupt the current emulation process. Oh, that's all. Thank you.
Thank you very much. That was so I'm really impressed by how much you're able to squeeze out of a single programmable switch. That's quite impressive, packing all of that into the switch. Did you run into a lot of problems with the development of that approach?
Yeah, actually it's okay because
what I mean, were the tools sufficient? Were the tools good? The tools that you used, were they good in helping you debug your programs and so on?
It's okay when we develop the TurboNet, but one challenge is that the link delay emulation is very difficult because we think that link delay emulation is very important because link delay is an important property, but it's also difficult to delay packets in programmable switches. At first, we think of many solutions for delay emulation. For example, we try to let packets pass the pipelines many times to just their delay, but this wastes too much bandwidth. And later we think of maybe we can use the delayed queue and utilize the queuing time to increase the delay.
So what kind of network metrics are difficult to emulate in your system? For example, can you handle congestion? Can you study congestion in your emulation?
I think congestion is not a property that we should emulate, but users can define their programs, their P4 programs on each emulated switch to construct congestion.
And how will that manifest itself in your? This is basically based on a question of Zhangji Jia, so how would that manifest itself in your emulator, the congestion?
Oh, the congestion, maybe we can, maybe it can be manifested by the queuing time on the corresponding queue. Maybe we can use some techniques such as the INT to output the specific queuing time so that to tell the users that there is congestion.
I see. Okay. So I think it's time for live questions. If anyone wants to jump in with a live question, go ahead. Is someone jumping in or not?
Maybe I can ask a question.
Yes, okay. Thank you.
It's maybe a bit naive one, but I understand why you're trying to use a single switch, but can you talk about using this emulation approach as opposed to building a network of actual multiple switches? Is it only the issue of cost, or why would you do what you propose as opposed to building a real network from real switches?
Sorry, can you pardon, please?
Yes, so instead of using a single switch to emulate the network, why won't you just build an actual network interconnecting actual separate switches?
So you say that we use the programmable switch to emulate the network, so the each network device is expressed by the P4 program. So maybe we cannot reflect the hardware issues. It's a inherent problem of our method. That is, we use P4 program to represent the network device, and we cannot reflect the hardware issues.
Okay, thank you.
Okay, I'm going to ask another question. So how do you sort of verify that your numbers or your measurements are, you know, realistic?
You mean what kind of measurements?
Well, I mean, how you're trying to emulate real networks. Yeah. So how can I be sure that the measurements are realistic in terms of, you know, if I built the real network, then the results of your emulator would be more or less the same. I mean, how am I guaranteed that?
Yeah, just as I have mentioned, we use one programmable switch to emulate the network, and we suppose that all the network devices are the programmable switch. So that is, we emulate a network that is composed of multiple programmable switches. We use one programmable switch to finish it. But since we use the port mapper and Q mapper to finish the port mapping, and the results should be correct because they are isolated in our programmable switch.
Right. But to actually test it, I guess you would need a handful of programmable switches, and then that's quite expensive, isn't it?
Yeah.
Right. Okay. Okay. I think thank you very much for an interesting talk, and I think we're gonna thank the speaker. I think you only heard one person clapping. That was me. Okay. Thank you. So let's have the next speaker, who happens to be sitting in the same room.
Yeah, I use my laptop.
Okay, so hello everyone.
Yeah, let's just wait let's wait a minute so that
hello everyone. Yeah, can you see me? Yeah. Okay.
Okay, so hold on a second.
Yeah. Actually, I'm going to change the remark from Jiamin to Shuhe. Okay, wait a minute.
Okay. So the next talk, coming from the same office, is going to be Shuhe Wang talking about a system called Martini. And Shuhe, I hope that you will start by introducing yourself, saying a little bit about your background and what kind of research you're doing.
Okay, yeah, okay, so wait a minute, I'll just rename myself to Shuhe Wang. Yeah, okay.
Okay.
Okay. Yeah, it's interesting. So, okay, I'm also a third year PhD student from Tsinghua University, and I'm actually from the same lab. as Jiamin, and my research interests includes programmable network measurement, and network programming. Okay, so today I'm going to talk about Martini, the network management framework that bridges the gap between network measurement and network control with programmable switching ASICs. And this is a joint work with multiple institutes, including Peking University, Clemson University, Alibaba Group, Barefoot Networks, and Huawei Technology. First, we pick into how traditional network management organized. Traditionally, the network management is composed of three aspects: the measurement, decisions on measurement statistics, and control and actions based on decisions. There are a lot of applications in each aspect. For example, in measurement, there are detections on heavy hitter, super spreader, flow size distribution, black hole, packet loss, etc. The decision, based on all the collected statistics, may do analysis on anomaly detection, route optimization, fault localization, etc. And based on the decisions, the control will reconfigure the network. For example, adjust link weights and access control list, redo the load balancing, etc. However, we can see from above that currently these aspects are separately implemented. From above, we can see that the data are collected in the underlying distributed switches, while controllers periodically pull or switches regularly report them to the controller. So the data are analyzed in the centralized controller, after which network control is finally issued to switches. However, this inevitably leads to a long, untimely control loop. And we show the common control loop from first measurement to final control. First, switches will periodically report to the controller, and the report interval usually takes milliseconds to seconds. For example, OpenFlow reports flow counters every few seconds. Then, when begin reporting, the switch pipeline first sends statistics to the switch CPU, which then communicates with the controller, while the return flow rules follow the inverse path. And this part could reach tens of milliseconds. Next, statistics and control rules are transmitted between the switch CPU and the controller, and this also takes milliseconds to microseconds. Finally, in order to reduce the communication latency and save bandwidth, switches always send encoded data to the controller. So there should be a process to decode data and make decisions based on them. In our setting, we use sketches for measurements, and controllers will use techniques like reversible sketch, group testing, and so on to retrieve all the flow keys, but this will also take seconds to minutes to accomplish. In summary, traditional centralized control plane for control decision introduces a long control loop. However, modern networks need to quickly react to measurement results for timely control. Here we list two representative scenarios. First is the timely heavy hitter control, whose goal is to drop large size flows in the network. Each network node will maintain counters of each flow, and once the packet value exceeds a threshold, this flow is considered as a heavy hitter. We require to quickly detect this heavy hitter and control it with adaptive rerouting, rate limiting, or any other ways. However, current centralized implementation reports flow counters to the collector at fixed time points, which may be unresponsive when heavy hitters appear. Another example is in video congestion control. When the congestion happens and an I frame is dropped, all its subsequent P and B frames become useless and should be dropped. But in current implementation, to maintain the state machine of the task, the controller needs to identify the current network state and issue commands. This delay in the whole control loop may cause unnecessary frames to buffer or drop correct packets. So the long control loop has indeed impaired many latency-sensitive management tasks, and existing works try to address this gap. One group of study proposed to enhance switching ASICs with more functions towards specific tasks, but they not only lacks generality, but also needs long development cycle to redesign the ASICs. Another direction is to place controller in local switch CPU. However, most parts of the control loop are still not eliminated, and the controller can only pull statistics at fixed intervals, which is unable to monitor data plane at any time. There are also studies that enable the data plane to directly detect network events based on measurements, but the events still need to be handed over to the controller. The main problem is that we still need a controller to make decisions in general conditions, but we also observe that a large portion of tasks require only local measurement results for decision. Therefore, if the switches can automatically carry out different control actions based on measurements, the decisions can be moved to the data plane and the controller is no more in need. With the use of current programmable switches, we can flexibly design all the measurements and control we want the switches to execute, and dynamically do the decisions to map them together. So we propose Martini to offload all the management tasks entirely to the switch data plane and provide a general framework for users to manage all kinds of tasks. Martini provides a complete framework from top to bottom. First, it provides a set of high-level management task description primitives for operators to easily describe and assemble all three management phases. Second, Martini provides an innovative network-wide task placement mechanism to exploit resources of all network switches for massive management tasks. Finally, Martini provides a library of measurement and control components and a compiler which automatically composes them to generate programs on programmable switching ASICs. And we will introduce these parts separately. So first, here comes the first challenge in task description. Although recent studies have proposed languages for either measurement or control, they are not considered collectively. How to use an easy and unified scheme to describe the whole task. We propose to use modular primitives to just describe each phase separately and stitch all phases in a line. In measurement, most tasks can be reduced to composition of several basic primitives, such as filter, updates, query, group by, and temporal primitive like window. In control, since it spans across multiple different fields such as scheduling, routing, congestion control, etc., we simply encapsulate common ones into modular primitives, and users can add new primitives for new control at any time. For decision, since it detects network events based on measurement statistics, we can simply use conditional expressions to express the phase. However, there exists another problem that traditional measurement primitives update and query in a row. But for example, in DNS reflection attack defense, we should maintain records when receiving DNS requests and separately query the records when we receive DNS response. Therefore, we decouple the update and query and add an additional filter stage to lead one set of packets to update the record only, and the other side to query or group the records only. For other detailed explanation of the primitives, please refer to our paper. So here we give an example of the task description using the DNS reflection attack defense that we have just mentioned about. And we can see that with only 6 simple lines of code, the user can clearly define the whole scope of the task and leave the arduous implementation detail to Martini. To convert the high-level description into concrete implementation on switches, the underlying realization for each modular measurement or control task should be clearly specified. So our second challenge is to implement all the different types of tasks onto programmable switches. Since the switches have limited resources such as SRAM and stateful ALU, and measurement tasks just require a summary instead of the whole statistics, and they don't require 100% accuracy, we can therefore use sketches as the underlying data structures. Sketches are essentially register arrays that project high-dimensional data to small subspaces, and it can be updated with a group of hash functions in a per-packet way, and always guarantees error bound with given memory space. And these features actually imply that sketches are suitable to implement on programmable switches. And referring to the prior work like OpenSketch, we have implemented all the common sketches that are used in current measurements. For example, the bitmap that holds the existence of flows, the counting sketch that holds the upper bound of the number of flows, the key array sketch that estimates the difference between two intervals, the PCSA that uses a bunch of small registers to estimate the flow size roughly, and the multi-resolution classifier that holds the flow size distribution of multiple flows. And there are many more of them, and we will open source the code later, and you can refer to our code to see their implementation tricks. And here we want to introduce one implementation trick that is generally used among all kinds of sketches. It is a common operation to aggregate statistics within a time window in measurements. However, current switch programming languages such as P4 don't support timer or batch clearance for counter errors. So therefore, we use the round-based mechanism to approximate the window primitive. We set each round as a fixed interval, and counters are cleared across different rounds. In the switch, we store the current round and its start time in local round indicator. Once the difference between the ingress packet timestamp and the start time of the current round exceeds the window length, exceeds the window length, we will move to the next round. And we also append each counter with a separate last time updated round. If it's here, and if it is below current round, it is reset to the current, and the related counter will get cleared. And in our implementation, the counters are usually 4 bytes wide. To save as many switch resources as possible, we will set the round to be 8-bit wide, so the resource overhead will only be 25%. However, an 8-bit round covers at most 256 consecutive intervals. So if the difference of the rounds of 2 consecutive packets is the multiple of 256, they will have the same current rounds due to wraparound, and this will cause mistakes. Nevertheless, we will later show in our evaluation that the error rate of these techniques is extremely low. Next, we will discuss how to establish the mapping from high-level primitives to user-agnostic low-level implementation. To do the compilation, we should first know how many resources does each primitive consume. Since the primitives are modular, we can separately estimate each single phase. First, we map the common composition of measurement primitives into the sketches we implement and calculate the resources they take. We can see from the table that flow size, error rate, and threshold all have influences on resource consumption. Next, the decision phase only occupies 1 pipeline stage and negligible SRAM resources as a single conditional expression. For control actions, we examine their implementations and find that the pipeline stage is the critical resource. As the previous slide shows, measurement and control may consume many SRAM and pipeline stages, and one single switch may not be sufficient to provide all the resources. But fortunately, we observe that a flow may go through multiple switches before reaching its destination. So we can split the task into subtasks and distribute them onto the switches alongside the flow forwarding path to correctly manage the flow. We use 2 ways to partition the task. One is computation partition, which splits tasks according to its execution phases, while reserving their orders. Also, we couple measurement and decision, since decision consumes almost no resources and can directly based on measurement to detect events, which saves lots of bandwidth rather than sending all the measurements to Dixie to control. Another way is to do data partition, which uses multiple instances of the same task and equally divides the flow into individual instances. As the resource usage is related to flow size, this will release the burden for one switch to monitor all the flow. Given the partition task, the network topology, and all the resource estimation, we can model the placement problem into an integer linear programming problem, as there already exist many material ILP solvers, and we can just use them to solve the problem. To form this problem, our intuition is that management tasks should occupy minimum switch resources. Since subtasks can share a pipeline stage if the other resources within this stage are sufficient, we choose to use the stage occupants as the optimization goal. We formalize the resource constraint and the ordering constraints between tasks, and with the model's output, all the subtasks can get distributed along their forwarding path. And finally, the compiler can generate concrete low-level P4 code to the switches. Here we introduce one trick, and for other tricks, please refer to our paper. Under computation partition, events should transmit between phases. If the 2 phases are placed in different switches, we can modify the packet headers for event delivery between switches. However, adding new header fields may hurt the good put. So we exploit the unused bits in current headers, such as the VLAN identifier field, to append the detected events. As this field is 12-bit wide, it can hold at most 4,060 and 96 types of events. And all the types of events can get encoded in theory, which is already enough for our management. Finally, we evaluate Martini on a real test bed, in which each Tofano switch is connected with multiple servers, and 2 switches are directly connected. We have realized 4 schemes, including 2 strawman solutions, which separately perform control decisions in remote CPU and in local CPU, and 2 Martini implementations. separately on a single switch or span across two P4 switches. So under the 4 schemes, we have implemented 16 common management tasks in roughly 4 task types. Martini makes it easier to describe management tasks by composing primitives. And it usually takes less than 10 lines of code to describe a task. Well, in P4, it will require you around 30 more full lines of code. And we choose 3 representative tasks and measure the latency of each component in the control loop. As shown in figure A, the communication latency takes at least millisecond delay. In comparison, Martini completely avoids this latency. As shown in figure B, the controller needs to decode sketches to make decisions. And this takes as long as 3 minutes. Since Martini implements entirely in the data plane, it avoids the K deriving part. In figure C, we present the total control loop in traditional and Martini patterns. The control loop of the traditional patterns is 2 to 4 seconds. For the Martini one switch case, the control loop is within one single pipeline stage, and it will take only around 10 nanoseconds. For the Martini two switch cases, the control loop will grow to around 370 nanoseconds due to the event queuing and wire transmission latency. However, this latency is still small compared with the two Strawman solutions. To test compilers' efficiency, we implement the algorithms in a server and simulate the topologies of 3 real-world networks in the above table. The offline compilation time is mainly composed of 2 parts: placement running time and code generation time. We perform 2 processes in all 3 topologies. And our evaluation result shows that both times increase linearly with task numbers. And with even as much as 20 tasks, both times are still within 1 second. So Martini's compiler is able to run within reasonable time. To demonstrate that our placement algorithm can yield the best resource usage, we compare it with 2 Strawman solutions, namely the ID first, which always places the next subtask to the next available switch in the forwarding path, and cross first, which always places the next subtask to the switch with the most number.
Something wrong here?
It seems we have a problem. Perhaps we can get that session back. Shuhe, are you still there?
Yes, they had the same problem.
Oh, yeah.
Another speaker dropped out due to the system crash, I guess.
Oh, okay. Well, maybe they'll be back soon. Just let me say this in the meantime. I hope I'm using this question and answer thing correctly. I'm a little worried because I've seen no questions in this session. If anyone out there is asking questions and they please tell me, jump in live right now and tell me that you've asked the question, because I don't see any questions posted. While we fix this problem, somebody volunteer to just type something into the question thing, just as somebody in the audience, just type a random question in, just so that I can see that it's working. This is a test, I see from David Husher. No, maybe David and Juan said, is this a question? Okay, so we have questions working. That's good to know. So now I want to see some real questions. Let's hope that Shuhe gets back. In the meantime, let's just wait. I think we have time. I'm going to foreshadow a question that I'm going to ask. Because if I were, let's say, programming a network using Martini or programming various management tasks, I would worry a lot about introducing oscillations into this dynamic control plane. Because often the problem with control in a network is that the control, essentially the time it takes for the control loop can have some sort of relation to what happens actually in the data plane, that you can actually introduce serious oscillations, like, you know, flapping back and forth between utilization of a single link or things like that. And those kind of oscillations are often extremely difficult to predict in advance. And so my question would be to, how can we detect those at sort of at compile time, let's say, and you know, is there a way of avoiding that kind of oscillation? I don't know. Do others have questions along a similar line with this kind of approach? Francesco, how are we doing on the recovery of this session?
I see one where the first speaker is back. I guess the current speaker should be able to use her machine, I guess. I don't know.
Yes.
Yeah. Hey, hello. Can you hear me? Yeah. Yeah. I'm sorry. Yeah.
Yes.
Yeah. I'm sorry. There's abrupt change. The computer is facing a battery shortage, and it just shut down. Yeah. I'm sorry. Okay. Yeah.
Okay. Can you show your slides again and pick up where you left off?
Okay. Okay. So I'm sorry. Okay. So I believe.
Can you share your screen?
Sorry. Yeah. Okay. Just wait a second.
Okay.
Yesterday, the same thing happened, so the speaker ran out of battery in the computer. I guess that's one announcement we should make in the beginning of each session.
Have your
keep the computer running.
Okay, let's carry on where you left off.
Okay, can you see that? See this slide?
Yes.
Yeah. Okay. Yeah.
Thank
you. Yeah. Okay. I believe here is where I just dropped. Okay. I'll continue. So to demonstrate that our replacement algorithm can yield the best resource usage, we compare it with two strongman solutions, namely the ID first, which always places the next subtask to the next available switches in the forwarding path, and cross first, which always places the next subtask to the switch with the most number of tasks in the forwarding path. We can see that compared with the two solutions, Martini always used the least number of pipeline stage. And the more tasks there are, the more benefits Martini can have, actually. And finally, we demonstrate that the trick to implement round-based measurement window is practical to use in real-world cases. Here we evaluate the percentage of faulty counters by varying measurement window and count packets that cannot trigger correct counter clearance by identifying packet pairs whose round difference are multiples of 256 measurement windows. The result shows that the percentage of packets that cause error increases as the measurement window decreases. And even if with small window as 10 microseconds, the error rate is only 0.2%. And this is actually acceptable in our setting. In conclusion, we have realized a general framework for timing network management on programmable switches. We provide task description primitives and the code library for common measurements and control components for users to use in a simple and flexible way. Our network-wide task placement deploys a management task into the entire network with high resource efficiency. And finally, our evaluation shows that Martini can reduce control loop from seconds to nanoseconds. And that's all. Thank you.
Okay, thank you very much. It's time for questions. I would like to start with a question.
Okay.
One of the problems is, I imagine myself as a network operator using Martini, And one of the things that I would worry about is introducing oscillations into the network.
Okay.
Because the control loop time may essentially cause route flaps, or link flaps, and other kinds of oscillations in the network. Isn't that a problem?
Yeah, actually, I think this is a good problem, but I think there are, I believe there are some works with programmable network that discussed how to ensure the privacy and the security and the isolation in data plane. I believe like P4 weather, they add another tag to identify the to match with different flows and isolate with different flows. Actually, I think we can also implement such similar techniques in the match action tables or in the packet headers to identify different flows and to handle them separately.
So let me make my question a little bit more concrete. At the very beginning, you showed an example of looking at a heavy hitter and essentially diverting that traffic to a specific link, right? But now suppose the control on that new link sends it back to the other link, and so on, right? And you get this oscillation of traffic between these links. How do you prevent that kind of thing?
Okay. I mean that okay, actually, okay, let me see. So you want to so if there's a heavy hitter happens, you want this heavy hitter to be diverted and without affect the other links, right?
Well, yeah, I mean, the thing is, what I'm saying is that there could, let's say you're going from link A to link B. You divert the heavy hitter from A to B, but B may have some other policy on it, not necessarily a heavy hitter policy. It may have some other policy that sends that back.
Okay, so are you talking about the task placement algorithm in Martini? It's to use so the issues in using multiple switches. Are you talking about this issue?
No, I'm just talking about any kind of control is got to have some kind of analysis of essentially some sort of feedback loop is possible, some sort of deleterious feedback loop, and I just didn't see that in this in your approach. I mean, I'm sure I can define some things using Martini that just make the network melt down, right? So you would really like some sort of compile time analysis of the Martini configuration that would alert one to that possibility, for example. That's just an idea. Maybe it's that's kind of future research idea. Perhaps.
Okay. I think I'll think about it. Yeah.
Okay, great. Let me just check right now. There don't seem to be any other questions. So I think we can start setting up for the next talk. Let me see if I can. I can't. I'm gonna thank you very much for that talk.
Thank you.
And let's set up for the next talk. This will be Zhong Huan.
Yes.
Hello. Are you?
Hello.
Are you ready?
Let me share my screen first.
Okay. So I'm going to first congratulate you on the Best Paper Award.
Thank you very much. Actually, that's a great honor.
And I'd like, could you please introduce yourself and tell us a little bit about your research and your research group?
So yes, I'm Zhong Huan, a senior researcher at the Network Security Group at ETH Zurich. And my research interests include future internet architecture, network security, and network virtualization. Actually, I've been working on this project for 4 years so I'm really glad to introduce our project and all the effort we put it in. And then finally, it seems like it got rewarded by getting the best paper already from this great ICMP conference. So may I start my presentation?
Yes, you may start. Thank you.
Okay, so good day, everyone. Thanks for attending this presentation. So as I introduced myself, I'm Zhou. And as one of the initial member of this project, we are working on more than 4 years. I'm so pleased to introduce you the Scion Lab, an exciting network testbed for network researchers. So as researchers, we are pursuing new scientific discoveries every day, motivated by unsolved problems, come up with new ideas, and proving them through experiments. To do so, having a proper laboratory is essential, right? For network researchers, we think the laboratory is a network testbed. The current internet is being used by more than 4.5 billion active users with the daily usage of 6.5 hours per day and the traffic generation of 88 terabytes per second. Our society, industry, and the government are literally dependent on the internet today. At this moment, I'd like to remind you that, as you already know, the internet was born in the 1960s as a research testbed. This is a good representation of how a well-designed network testbed could impact on our daily life. Network testing can be broadly categorized into 2 approaches, network simulators and the real-world testbed. Network simulators or emulators are virtual environments that abstract and mimic the behavior of a live network. Since they are a controlled environment, of course, it is relatively easy to conduct a large-scale experiment and even possible to reproduce the experimental result. However, the abstraction cannot perfectly model every aspect of the real-world environment. In contrast, a real-world network testbed provides exposure to non-determinism and the real-world effects. The price to pay is the lack of reproducibility and the higher cost in terms of deployment and the management. So our goal in this project was to create a new real-world network testbed that enables research in the following exciting areas: the pass-aware networking, the multipass communication, and secure interdomain routing. Pass-aware networking enables end host to select the passes leading to the destination. Pass-awareness offers exciting properties to applications such as pass transparency, fine-grained pass control, fast failover, and route optimization. Pass-aware networking also enables multi-pass communication. In case the end host obtains the multiple passes from the network, it can select the pass on a per packet basis. Multipass communication can provide increased bandwidth, improved reliability, and a more efficient link utilization. And the built-in trust establishment and the key distribution mechanism also provides a defense against network attacks, such as a denial of service attack. So here we introduce a new playground for network researchers, a Scion Lab, which enables secure and fine-grained interdomain routing control along with a true multipass communication. The Scion Lab is built on top of Scion, a future internet architecture. Scion is a path-based network architecture, so the Scion control plane is responsible for inter-domain path construction and dissemination. It explores networks to construct a path segment and concatenate them to create end-to-end forwarding passes. In the data plane, end hosts select passes and forward the packets via these passes. Each packet contains path information at the AS level. And the embedded PKI support control plane security. And the data plane verifies the validity of forwarding information of each packet. So back to the Scion Lab. Scion Lab consists of mainly three parts: global infrastructure, a user infrastructure, and the coordinator service. The global infrastructure is a group of autonomous systems forming the testbed core network that provides the intercontinental routing opportunities through the diverse passes. The ASs are launched in well-provisioned physical environment with a rich connectivity, so they provide a multitude of path options. The AS connectivity is realized in three ways. Ideally, the infrastructure ASs are connected through native Scion links. The Scion-enabled border routers, or software-based border routers, are paired with a direct layer 2 connections, achieving high speed of packet forwarding. If the direct pairing is not possible, for example, the two AS nodes are physically far apart, an IP overlay is used to create the logical link connectivity. Some links come with the Scion IP redundant links that support both Scion native connectivity and the IP overlay. Operating and managing such a global environment is often time-consuming. To achieve management scalability, we introduced the Global Coordinator Service, providing network operators with a simple web interface. Through the interface, operators can create or remove ASs and connections and apply a network policy for each AS. Once a new configuration is set, the coordinator migrates the infrastructure accordingly using some automation tools. The coordinator also provides a user web interface. By simply joining to the system, users can create ASs on their own machines. We call this bring your own computation. With bring your own computation, users can avoid computation resource scarcity by bridging as many resources as they need for their experiment. Once a user AS is initialized, the coordinator informs the user selected attachment point, and the attachment point creates a virtual link to the user AS. So basically, the Scion Lab creates IP overlay links for user ASs so that users can create ASs regardless of where their machines are. For machines with a private IP addresses, Scion Lab uses a VPN connection. Researchers set up a full-fledged AS participating without the limitations in the Scion Lab control plane. So user can create, configure their its own fine-grained routing policy and interact with the rest of the network. So now I'm going to show you a demonstration of Scion Lab. So we are offering a web service, ScionLab.org, where anyone can easily sign up to create their own AES and connect them to the testbed. After logging to the system, users can easily set up their AESs with an intuitive configuration interface by selecting the installation type, the link type, and the attachment point. Once the AES is created, the user can download the initial setup file by simply clicking the download button below. As you can see here, the old installation is fully automated, very easy to set up. The installation time varies depending on the user's network, since it automatically downloads all the required files during the installation. But with a fast connection, it just takes a few minutes. So for helping the newcomers, we created a tutorial page that describes how to join the Scion Lab and how to use it in detail. So it's already done now that we are in the Scion Lab AES and about to start science services. Just wait. Now we're checking the status. So everything looks fine. And as you can see here, the new AES is now receiving control plane messages from the Scion Lab core network, which means this AES works properly. And then you're ready to explore Scion Lab. And okay, and I'm going to show you another demonstration on how to run a Scion application on your AES. The Scion tutorial also provides explicit instructions on how to try out several Scion applications. In this demonstration, I will show a Scion Lab measurement tool. We call this a web app that visualizes the network performance. By simply following the instruction, this is quickly done. Let's check if everything is properly set up. So just keep in mind that again, all the commands you need are on the tutorial page. You can just simply follow the instruction. So it seems okay. Now we are opening up a new browser from the host machine, not the guest machine, actually Scion Lab running in the virtual machine on this laptop. So it illustrates the diagnosis result of the given AES, and in the other tab, we can see what kind of the passes are available between the AES and the rest of the network. You can choose all the different pass combinations and visualize them. Just keep in mind that those passes are real, so which means that you can leverage any passes for your communication. So here is a brief history of Scion Lab. Thanks to our close collaboration with academia and industry, the size of the Scion Lab has grown every year, and the successful expansion can be categorized into 4 phases. In the first generation of the Scion Lab, we focused on building a network infrastructure with global connectivity. And 1 year after, the network achieved connectivity across the Northern Hemisphere. In early 2017, we introduced a global coordination service that supports automated user AES installation on heterogeneous systems such as VMs, x86, ARM devices, and even on Android devices. The introduction of the coordinator facilitated the creation of user AESs. Today, we have more than 600 user-created AESs, and among them, over 90% are still active. A key property of the third generation of Scion Lab is the network backbone. We built a backbone network by leveraging the AWS EC2 instances and their internal network, which provides more interesting routing passes with much smaller latencies compared to the current internet. Now, we are in the first evolution of Scion Lab. Our ambition is to replace the current AWS backbone with a global research network, such as Jiamin, TurboNet, and Internet 2. The network, the research networks have a global connectivity and are well provisioned, offering a low latency and high bandwidth. Furthermore, they also have a rich connectivity with other research networks across the world. Therefore, it would enable all the Scion Lab users to conduct network experiments with a better path diversity, high performance data transmission, and low latency. To optimally support research, it is also important for Scion Lab to deliver a good performance. This figure plots latency inflation and depletion of Scion Lab compared to the legacy IP network. For one-hop communication, approximately 83% of node pairs shows a tolerable latency overhead of fewer than 5 milliseconds. For multi-hop communication, a third of node pairs achieved a better latency than the legacy internet. The improvement of the network latency mainly comes from the node pairs that benefited from the path awareness. For example, to forward packets from the Europe to East Asia in the legacy network, the packets typically travels over to North America, which is a serious detour. In contrast, a Scion Lab allows a more direct and latency optimized path. Interestingly, Scion Lab achieves better latency for a majority of node pairs with latencies exceeding 200 milliseconds. These results highlight that the Scion Lab actually provides a new research opportunity where the researchers can benefit from the path awareness. For multipath communication, it is also important to provide diverse paths that are practically useful. To see this, we also evaluated a path stretch that depicts the latency overhead over an alternative path over the shortest path. Our investigation shows that approximately 60% of the passes have a practical alternative path with a path stretch below 1.4. To see how much delay is introduced by our software-based board router, we conduct micro benchmarks on packet processing time. Although the packet processing time varied depending on the packet size, for an iMix distribution, over 90% of the packets are processed in less than 20 microseconds, which is considered as a practical processing delay even for the legacy routers. In the paper, you can find additional information such as implementation and deployment details, more experimental result, and lessons we have learned during the last 4 years of operation, and ongoing project running on the Scion Lab. Are you interested in joining the Scion Lab testbed? Please visit our website. For those who want to simply just try out a new network testbed or who don't have a dedicated hardware, we offer a chance to become a user AS using your laptop within a few minutes. did you want to learn Scion Lab AS 24/7? It is also possible to participate in the testbed as a part of the infrastructure. So thank you for your attention, and I'm happy to take your questions.
Thank you very much for that interesting talk. So I have a question that I think probably is on the minds of a lot of listeners. Could you compare this lab to things that people are familiar with, such as Planet Lab? Like, how would you compare your approach to Planet Lab?
Exactly. So first of all, the main difference between the previous the testbed, like a Planet Lab or the Genie, our testbed have a distinct, a unique identity that provides this bring your computation property that allows the users can add up their resources to the testbed, so that the testbed itself is not suffering from the resource exhaustion. For example, it is on Planet Lab. Users need to acquire resources from the testbed to initialize their slice, you know, the virtual slices. But there is always a long queue to get one. It's really sorry. It is really difficult to get one. So we call it these resource sharing difficulties. So we do Scion Lab we design and we intended to have this bring your own computation property to solve the problem. So as I mentioned earlier, the users can bring their own computation to create their own AES, and they are fully fledged to interact with the existing infrastructure, testbed infrastructure.
Okay, that brings me to a question asked by Chen. He asked, does Scion Lab support new generation of network devices such as programmable switches?
To be honest with you, I'm not quite familiar with the programmable switches, but as long as these switches support is running on the ARM architecture or x86 architecture, it's possible, I guess.
So all the nodes have to be running the Scion protocol. Is that it?
Sorry, Scion protocol. You mean?
Yeah, the Scion protocol. Every node is running the Scion protocol. Yes.
Yes, exactly. Basically, that's the principle. But to support just normal users, we also supported the IP overlay based Scion protocol. So there is no need to change any network stacks on the user devices.
So I have a question about the Scion architecture. How does it compare to something like segment routing?
Actually, yeah, that's a good question. Scion actually follows the notion of the segment routing. In the control plane, the Scion control plane explores network and they gather the network segment information to create the forwarding paths. And we broadly segmenting the network in three pieces. The up segment that represent the segment between the end AES to the core AES, and the core segment that represents a network segment between in the core AESs, and the down segment that means the network segment from the core network to the customer AES, for example. So we concatenate these three pieces of this path segment to create one single forwarding path. So I can summarize that the Scion Lab follows the notion of the segment routing.
Okay, so what kind of experiments are your current users doing with on the platform?
So there is a many researches running on our testbed. For example, Scion Lab, since Scion Lab provides the multipass communication property, that it allows users to use the multiple passes for a single communication, which means that the end user can achieve a better high speed data transmission. So that is the one of the research ongoing, and another one is about this fast packet filtering that leverages the Scion embedded Scion PKI system, because Scion offers the secure control plane control plane environment. End users can also leverage this property to make the communication secure. And yes, and the another one is about the monitoring system that surveillance the communication which uses multiple passes. Compared to the typical notion of the network monitoring is that mostly they are relying on the flow-based monitoring system. But in the multipass communication, it uses different passes for a single flow. So it's really hard to adapt the previous monitoring system to the multipass communication environment. So actually, this is a new research area that the Scion and the Scion Lab enables.
So imagine I'm using the lab as a, I'm just browsing the web through an overlay on the lab. Obviously I don't want to be worried about the best path and so on. So at what point in the networking stack am I going to be making those kind of decisions, right? I'm going to do that in an automated way.
That's a great question. So definitely end user, just a normal user, don't care what path they're using, but the application providers can provide the better path for the user experience. For example, for gaming, the low latency is really important. So the game game production studios can create their online game streaming platform that select the best low latency path, than just follow use the legacy IP packet.
Yeah, and so what kind of API is there? Let's say operating system API for actually gaining access to that information. How do you, how does an application get at that information?
So in our implementation, Scion itself is running in, I can say, similar to the layer 3 protocol. So it is positioned in the layer 3 level, and we also provide the daemons called Scion daemon. The Scion daemon provides the API between the application to the network stack, so that the Scion can provide different passes with the various network properties. For example, low latency, high bandwidth, or low loss rate, or jitters, something like that.
Does that mean that every host has to participate in the routing, or no?
No, actually, in Scion Lab, we provide a chance to become an AS, right? Which means the user would have a full control over the AS. For example, establishing some routing policies and everything. And it's also possible to run a virtual end host on top of this AS. So literally, user has a full control from the application layer to the network layer.
I see. That's very interesting. Let me just check that I don't see any other questions. Would anyone like to jump in with a live question? everybody is shy.
You mentioned you are let's say attempting to replace the existing testbed. Did you consider the other testbeds, like I'm running the Planet Lab, for instance? Whether...
No, actually, we are not competing with the existing testbed. Each testbed has their own benefits and advantages. Our testbed is not competing to the existing testbed. Rather than that, we want to provide a new testbed that offers new research opportunities like pass-rail networking and the multipath communication and secure routing.
It's actually emulation based. Is that right? Emulation based, or the real? I didn't follow exactly, but I assume the users will based on your emulated or real hardware virtualized environment to do the experiments, or it's a lot of machines distributed in different places like a Planet Lab. What kind
exactly
of
actually yes
deployment requirement for your lab?
So as I mentioned earlier, that we have two different components in the Scion Lab. The one is the global infrastructure, is another one is for the user infrastructure. Global infrastructure itself is a physical, actual environment that we deployed the machines across the world. With the help from the participants. So now we have more than 35 ASICs, physical ASICs. They're communicating each other. So it's hard to say that our Scion Lab is an emulator. Actually, this is a real world testbed.
Are there any other questions out there? Live questions?
Yeah, one question from Alex Gallis, University College London. The testbed looks very impressive.
Thank you very much.
Very much so, yes, and continues. So it's a lot of work and good work and excellent results. However, if you look in terms of history of such a testbeds, which have more than 60 years now, of many testbeds in the area, they tend to go into the subjects of, or many subjects, including management, which is missing in your, and more importantly, sometimes linking it with the service area and linking it to service area with user space. In other words, a complete stack of big problems sometimes are needed to highlight some of the infrastructure issues which your testbed tend to focus on, which are needed for the future. The question is, what is the next step? Are you going to go to this additional big levels, management and services, network services at least, or not?
So that's a good question. So the next step of the Scion Lab will be, of course, the first, we want to have a more rich connectivity deployed across the world with a high rate of the native Scion connection. Actually, the current network is huge, but not that huge compared to the current internet. So to make our testbed and to the internet scale testbed, we need more collaborators, participants, and then we need to deploy more machines to create the actual Scion enabled, natively enabled environment. So currently, since there is only a sparse distribution of the our system, many links are overlay network. So they're purely affected by these underlying routing protocols such as BGP. But we want to establish the Scion native links. And in that context, we are envisioned to have a Scion backbone that fully established with a Scion only connection, so that we can get rid of these all the drawbacks that the BGP delivers. For example, a slow convergence and some congestion control and something like that. So that is our ambition for the Scion Lab.
Okay, thank you. Are there any other questions? I'll check the online questions. So I think that's about it. We're probably a little bit over time already. Thank you very much for a very interesting talk, and I hope you pick up some new users because of this talk.
I hope so.
That brings us to the end of this session. I'd like to thank all the speakers once again, and that's the end. Bye-bye.
Thank you very much. Bye-bye.